Okay, so this is Unit 5-6, Box C, parametric and vector equations of a line in the plane. Okay, and when we're talking about a line in a plane, it just means we're talking about something in 2 dimensions. Now, you've been working with lines in 2 dimensions since grade 9. Okay? And one of the first things you learned in grade 9 was that all it takes in order to define a line in 2 dimensions are 2 points. So let's say we have 2 points on our line here. -1, 1 and 2, 3. And we've got a line that runs between, that goes through those 2 points. So we'll just add this in. It's a straight line working its way through those 2 points. How can we use the coordinates of those 2 points to come up with an expression defining this line, an equation for this line? Okay? Our 2 points sort of define the line in the sense that there's only one line that goes through these 2 points. Define a line. Okay? How can we come up with a mathematical representation of this line using these 2 points? It's impossible, right? Yeah, equation of a line. Y equals mx plus b. So how would you determine what this thing slope is? Absolutely. So in this case, we'll use y2 is 3, y1 is 1. Okay, and our x2 is 2, and we're going to subtract our x1, which is -1 here, and we end up with a slope of 2/3. And then you would plug this into our equation here. You would work out what the intercept is, and you would get something that looked like this. And I think the slope works out to be 5/3. So we've got this equation that represents the line. What good is this equation? What can you do with this equation once you have it? I mean, you write it down as the answer to the question on the test, but beyond that, what else can you do once you have an equation for your line? Let's say I asked you for some other points that were on this line. Name 2 other points that are on this line. How could you do that? Jessica. Yeah, so you could put in one coordinate, solve for the other one. It's easiest if you put in a value of x. So just pick a random value of x, stick it in, solve for y. That x and y together give you an ordered pair that is a point that is on this line. Okay? From this, you could also check to see if another line was parallel or perpendicular to this by comparing the slopes. If you didn't already have the graph, you could graph this line using the slope and the y-intercept. Okay? So there's a lot of things you can do once you have an equation of a line. What we're going to look at here is how you can use vectors to come up with equations for lines, or how do you represent a straight line using an equation involving vectors. So what we're going to do first is we are going to use these 2 points. Instead of using them to find out the slope of the line, we're going to use them to define a vector that tells us the direction of this line. So we're going to use the points to define what we call the direction vector. Okay? And this direction vector is going to point along our line. So it's going to look something like this. Okay? And it's telling us, you know, what direction our point is going, our line is going. So we've got 2 points on our line, so we can use these 2 points to define ourselves a vector. And we'll call this vector AB, okay? And AB is going to be our end point minus our starting point. So 2 minus negative 1 is 3, and 3 minus 1 is 2. So if I draw this a little nicer here, okay, AB is the direction vector that starts here and it goes to here, okay, which is pointing along our line here. Now because AB is a vector, it is, like I could take this vector and I could put it anywhere, okay? I could slide it up, I could move it over here, because vectors, we can move them around at will. So if we want to specify this precise line here, we have to sort of anchor this direction vector to this particular line. And what we're going to anchor it with is a particular point that is on the line. So we're going to use a point on the line to anchor this vector to this specific line. Now what point are we going to use? Well, we could use any point that is on this line. Let's use, we'll use negative 1, 1 for our starting point. So we use negative 1, 1 here, okay? If we wanted to get a bunch of more points on the line, we could start from this point, negative 1, 1, go in this direction given by this vector, AB, 2, 3, and we could just keep going further along the line. So if we took this vector AB, made it twice as long, instead of stopping here, we would stop at some other point way up here, okay? If we just make that vector longer. And the way we can make a vector longer is we multiply it by some scalar. This vector from here to here would be a scalar multiple of this direction vector that we defined here at the beginning. Okay? So we can say, to get more points, or to get all of the points on the line, simply, what should we say here? Multiply the direction vector by different scalars. Okay. And whichever scalar we choose is going to give us a different point, because we're moving farther and farther along this line. Okay? So we can put all of this together into an actual equation for our line here. Okay? And this is what the vector equation of a straight line looks like. Okay? We've got a vector here, r, which is equal to some set of coordinates, x naught, y naught. X naught, y naught is just some point on the line. This is kind of like our starting point. Okay. AB, okay, which is our direction vector, which points in the direction of the line. And we take AB and we multiply it by some scalar, okay, to go further along the line or less far along the line, or the opposite direction along the line. Okay? And what this vector specifies in the end is the position vector of any point that is going to be located on this line. Okay. Let's get rid of this. Okay. So in our example here, that vector that we had, we could represent it as our starting point, which was -1, 1, plus some scalar times our direction vector, which was 3, 2. And that would specify that line that we had drawn on the previous page. Now, we could have chosen, like there's a lot of different equations that represent the same line here. We could have chosen a different starting point here. So we could have chosen the point 2, 3, which was also on our line. And in terms of our direction vector, we could have chosen any other vector that is parallel to the direction vector that we chose. So we could have chosen something like, 6, 4. Okay? That would specify the exact same line. Okay? So that is the vector equation of a line. Let's see. Oh, I got a picture here. Okay? So if this is our line right here, okay, what we've got to imagine is this line is made up of a series of points. Okay? And we want to be able to specify each and every point along this line. So a single point here, let's call this the point xy. What r represents is it represents the direction, the vector from the origin to some point on this line. Okay. So this is what r is. Okay. And imagine this point can sort of move back and forth anywhere along this line. So r represents any vector that points to any one of these points that is on this line. Okay? How do we get to this point? How do we get this vector r? Well, if we pick a point on the line that we know is on the line, that's our x0, y0. Okay? That ordered pair, x0, y0, is the vector from the origin to that point. Then we have our direction vector along the line, AB, and then we're just sort of scaling this up by some factor to get all the way up to xy. So if we take AB and we multiply it by some scalar, t times AB will take us along that line from our starting point, x0, y0, to our endpoint, xy. And that'll be the vector equation of that line. Okay. So, vector equation of a line. There's another form that we're going to talk about right now, and that's what's called the parametric equation of the straight line. Now, the parametric equation starts from our vector equation. Vector equation is almost always the easiest one to find, so you should probably find that one first. So if we start with our vector equation, which was some starting point, x naught, y naught, plus some scalar times our direction vector, AB, okay, where this is, of course, any point that is on the line. This vector here can be represented as the coordinates of any point on this line, xy. So if we break this up into our x components and our y components, for our x components we have x, x naught, and t times a, or this expression right here. If we look at our y components, I've got y is y naught, and then t times b, for bt. So these two things together, sort of splitting it into these two equations, this is our parametric equation of our straight line. So the parametric equation is just split into the two components, x naught plus at, y naught plus bt, where ab, again, represents our direction vector, y naught x naught is our point on the line, and xy is the position vector, or the vector pointing to any given point on that line. And t here can be any real number. So because we have an infinite number of choices for that parameter t, we get an infinite number of points on our line. Okay? So let's take a look at an example that we can do here. Okay? Example 1. Find the vector and parametric equations for the line through the point 3, 2 and 7, 14, and find two other points on the line. Then find out if the point 820 lies on this line. So they ask us for both forms of the equation here, vector and parametric. If they ask you for both, always find the direction vector first. The vector equation first. So our vector equation is, of course, going to look like this, where we need some point on the line and we need some direction vector. How can we find that direction vector? So to find that direction vector, yeah, we just subtract the 2 points that we have. We can take our endpoint minus our starting point, so we can do 714 minus 32, and we end up with 412 for our direction vector. Now what your textbook likes to do is anytime they get a vector like this, they simplify it, or they reduce it down to a vector that's kind of, it's like putting it in lowest terms, but they're coming up with a vector that is parallel to this, but has the smallest possible number. So they basically take each of their components here, divide them by 4, and they get the vector 1, 3. Okay. These are the same vector, but they just like keeping things as simple as possible, I guess. So we've got our direction vector. How can we put this together into an equation, or vector equation here? Well, we need some point on the line. What point do you want to use? Ronnie, what point do you want to use? All right, let's use 714. So we got our starting point, 714, plus t times our direction vector, 1, 3. Didn't organize that very well, but there you go. That is the vector equation for our line. Okay. Now, find two other points that are on this line. How do we find two other points that are on this line? Well, this is easier to do once we have the parametric equation. So how can we take this and turn it into a parametric equation? Well, we just have to separate out our x and our y. So what are our x components going to be here, or the x portion of this vector equation? Well, what's the x-coordinate of our starting point? 7. To this we are going to add, what do we have to add to it? 1t or just t. Okay. What about our y? Starting point for y coordinate is 14. What are we going to add to this 14? Exactly, 3t. Okay. So this is our parametric equation here. This is our vector. This is our parametric. Now, finding two other points that lie in this line amounts to just choosing a value of t. Okay. So, pick a value of t here. What's the simplest value of t we could pick? We could pick, well, even easier than 1 would be 0. But if we put 0 in, we'd get 714, which we already have. So the next simplest is t equals 1. If I sub t equals 1 into both of these, I get x equals 8, y equals 17. So the point 8, 17 is on the line. What else could I sub in for t? I could pick anything I wanted here, any real number. I could pick a half, I could pick 3/4, I could pick 2 billion, whatever I wanted. But I'll pick something easy like -1. Okay? If I sub in t equals -1, I get 6, and y is going to equal 11. So 611 is also on R. The last thing we want to answer here is, what about this point 820? Is it on the line? Well, let's see if I can write this. 820. And I'll just put a question mark. Is 820 on the line? Easiest way to go ahead. Oh, yeah, I made that one pretty obvious, didn't I? Yeah. Let's choose another arbitrary point then. Is the point 3057 on the line? Here's how you would figure it out. If 3057 were on this line, 30 is our x value, 57 is our y value. So if we put 30 in here for x and 57 in here for y, there should be one value of t that satisfies both of those equations. Okay, it should be t equals, 5, t equals 8.7, who knows. So what we can do is we can start with one equation here. Let's start with our x equation. 30 equals 7 plus t. What value of t does that suggest? Well, if we solve this for t, this is telling us that t should equal 23. We can do the same thing for our y equation. So y equals 14 plus 3t. So our y is 57 equals 14 plus 3t. Yeah, 14 plus 3t. And we can work out what t should be here. So 57 minus 14 is 43. So this is telling us that t should equal 43 over 3, which is not the same thing as 23. So since these don't give us the same value of t, we can conclude that this point is not on the line. Therefore, 3057 on the line R. Okay? Just because there's no single value of that scalar t that is going to give us both the x-coordinate and the y-coordinate. Okay? All right, we'll take a look at one more example here, and then we will stop for the day. We've got two lines given to us. R equals 2, 0 plus t, 3, negative 4, and x equals negative 1 minus 6t, y equals 4 plus 8t. And we're asked if these things are perpendicular, parallel, coincident. Describe how these two lines are related to one another. So we'll call these two lines line number 1. And to make them easier to compare, we should take this one here, which is in parametric form, and put it into vector form as well. So how can we put this into vector form? Well, it's sort of the opposite of what we did before. These two numbers here, negative 1 and 4, are going to give us our sort of our anchor point here, or a point that is on the line. And we're going to have t plus these two numbers here, the negative 6 and the 8, give us our direction vector. So negative 6, 8 is our line. So we'll call this one line 2. So we want to figure out whether these things are perpendicular, whether they're parallel, what's going on with these two things here. Let's check first to see if they are perpendicular. The way we can check if they are perpendicular is by looking at the direction vectors. Our first direction vector here, we'll call this d1 is 3, negative 4. Our other direction vector, d2, is negative 6, 8. Because these two direction vectors point in the direction of the two lines, if the lines are perpendicular, the direction vectors have to be perpendicular. So how can we check to see if these two direction vectors are perpendicular to each other? What do we need to check to see if two vectors are perpendicular? Arjun. Let's check their dot product. So let's do d1 dot d2, which is going to be 3, negative 4 dotted with negative 6, 8, which is going to be negative 18 minus 32. We're checking to see if this equals 0. If the dot product is 0, these things are perpendicular. This works out to be negative 50. Yes, negative 50. But the key thing is it's not 0, so they are not perpendicular. So our two lines are not perpendicular. Now we want to check to see if they are parallel. What do we want to check to see if these two things are parallel? Well, if the lines are parallel, what do the direction vectors have to be? Parallel or scalar multiples. So we want to see if d1, our first direction vector, is a scalar multiple of d2. Well, let's see. d1 is 3, negative 4. d2 is negative 6, 8. Is there a scalar, a single scalar k there, that is going to turn d1 into d2 just through scalar multiplication? So we've shown that these two things are scalar multiples. Therefore, we can say that our two lines, R1 and R2, are parallel. Since we can just say D1 equals K is a scalar multiple of D2. Direction vectors are scalar multiples. Well, they're parallel. Let's check to see if these two lines are actually coincident to one another. In other words, they're the same line. How can we check this? Any thoughts? The easiest way to do this is pick a point on one line, see if it's also on the other line. Okay? So let's choose a point on our second line, R2, and see if it is also on R1. What point do we know is on R2? The great thing about the vector form of this is that it always gives you at least one point that is on this line. And that's the point that we're using to anchor our vector here. So we know that the point -1, 4 is on R2. How can we check to see if it's on R1? Well, we can, excuse me here, we can sub it in. Oh, the way we checked that last time was we used the parametric equation. So we should probably do this the other way around. We've got the parametric equation for R2, so we should pick a point from R1 and see if it satisfies this scalar, this parametric equation that we have for R2. So let's just reverse this here. Pick a point that is on R1, see if it also is on R2. So the point that we know is on R1 is 2, 0. 2, 0 is on R1. We've got our parametric equation there for R2, which is we got x and y here. So we've got -1 minus 6t and 4 plus 8t. Okay. And let's just check and see if this point, 2, 0, satisfies this equation. Well, let's see. Let's do our x first here. So we'll do 2 equals -1 minus 6t. 3 equals -6t. T equals -1/2. Okay. And let's do the same thing for y here. 0 equals 4 plus 8t. -4 equals 8t. So t equals -1/2. So we get the same value of t, that same scalar, when we do both of these. That means that that line 2, 0 is on both of these lines. Sorry, that point 2, 0 is on both of these lines. Therefore, since they're parallel and they share a point, R1 and R2 are coincident. Okay. So you may remember doing this kind of question way back in grade 10, where they gave you the equations, the linear equations of two lines, and you had to figure out, are they parallel, are they intersecting, are they coincident, and so on and so on. Once again, everything we do in this course is just grade 10 math, done using vectors.